let's look at a more interesting example of finding a Fourier series. Let's find the Fourier series for this square wave. So remember that we're implicitly assuming the domain here is just from 0 to 2 pi, and we're assuming that outside of this domain, the function repeats itself. So, from 0 to pi, this function is 1, and then at pi, it suddenly jumps down to -1, like this. And then at 2 pi, well, now it starts to repeat itself, which means that it jumps back up to 1, and then goes back down to -1. You can see why this is called a square wave. It's because we have these square tops, these square crests and square troughs for this wave. So let's go ahead and find the Fourier series. Remember, to do this, we just need to find the inner product of this function with each of our basis elements, and then put all of those inner products into the big formula for a Fourier series, which again is just an expression of a vector in terms of an orthogonal basis. So let's calculate the inner product of, excuse the cat fighting in the background. Let's find the inner product of 1 with f. Okay, so this is the integral from 0 to 2 pi of 1 times f of x. And to do this integral, well, to do any of the integrals that we're going to need to do, we're going to have to break this interval into two pieces, because this function is piecewise. It is piecewise continuously differentiable. Incidentally, there are only discontinuities at these isolated spots here. In between, it's continuously differentiable. But because of the discontinuity here at pi, we're going to need to split this integral up at pi to be able to tell what's happening. So this is the integral from 0 to pi of f of x dx plus the integral from pi to 2 pi of f of x dx. So from 0 to pi, the function is just 1, so we get a 1 here, plus integral from pi to 2 pi. Well, now the function is just -1 from pi to 2 pi. And then when we do these integrals, we get pi and minus pi. So this is 0. Right. So this square wave doesn't actually have any component for this basis element. So this, in other words, this basis element doesn't appear in the Fourier series for the square wave. Okay. What this basis element really measures is what is the average level of the wave, and this wave is symmetric around y equals 0, and so the average is 0. So that's why this came out to be 0. Okay, well, now let's find the inner product of this function with one of our cosine waves. And this isn't always possible, but for this particular function anyway, we can actually do all of them at once by just having the multiple n in here. So cosine nx, inner product with our function. Okay, and as with all other cases for this square wave, we need to break the integral up at pi. So let's do that right away. Let's go integral from 0 to pi of cosine nx times f of x dx plus integral from pi to 2 pi of cosine nx times f of x. Okay, but from 0 to pi, f of x is just 1, and from pi to 2 pi, f of x is minus 1, so we get minus cosine nx in here. Okay, and then we need to work out each one of these. Okay, so integral of cosine, that's nx, that's going to be 1 over n sine nx from 0 to pi, and then minus 1 over n sine nx from pi to 2 pi. But at 0, pi, and 2 pi, sine nx is always 0. So all of these things just turn out to be 0. So this square wave actually doesn't have any components for any of these basis vectors either. Well, it has to have some non-zero components, because otherwise it would be the 0 function, which it's not. So we need to go looking in the sine basis functions to find non-zero inner products. So let's do that. Let's find the inner product of our function with sine nx. So this is inner product from 0 to pi of sine nx times f of x, but again, from 0 to pi, f of x is 1 dx, plus integral from pi to 2 pi sine nx times f of x, but from pi to 2 pi, f of x is minus 1. Okay, so now we can integrate. For this first piece, we're going to get minus 1 over n cosine nx from 0 to pi plus, there's one minus sign here, but then we get another minus sign when we do the integral, so this is plus here, 1 over n cosine nx from 0 to 2 pi. Okay, so minus 1 over n. So when we plug pi into nx, right, we get cosine pi n. We'll have to think about what that is. And then when we plug 0 into cosine, we get cosine of 0, so that's 1. Plus 1 over n times cosine of, now when we plug in, oh, this shouldn't be a 0 here, this should be a pi. Okay, now when we plug in 2 pi, we get 2 pi n minus cosine of pi n, just pi n. Okay. So let's see, we have a 1 over n cosine 2 pi n. We have a minus cosine pi n over n, and another minus 1 over n cosine pi n, so that's minus 2 over n cosine pi n. And then we have a plus 1 over n, right? Yes. Let me make sure I didn't miss anything. Minus, yeah. Okay, so now we need to think about, well, what are these? N is an integer, so cosine pi n might be plus or minus 1. On the other hand, cosine 2 pi n, well, 2n is an even integer, so here we have an even multiple of pi, and cosine of an even multiple of pi is always 1. Okay, so this part here we need to think about still, and then this part at the end is 1 over n. So the part at the beginning and the part at the end we can combine. So this is 2 over n minus 2 over n cosine pi n. And now there are two cases. Right? Now what happens depends on n. So if n is even, then cosine pi n, right, this is an even multiple of pi, and cosine at an even multiple of pi is 1. So in that case, we would get 2 over n minus 2 over n times 1. But this would give us 0 total. Okay? But when n is odd, then we get 2 over n minus 2 over n times cosine of an odd multiple of pi. But cosine of an odd multiple of pi is minus 1. So I think, okay. So in this case, we get 4 over n. All right, so the only non-zero components in our Fourier series are going to be the cosine, or sorry, are going to be the sine components. Remember, we were working out the inner product with sine, but only the odd components, not the even components. So let's just write down the first few of these. So this is going to be an infinite series, but let's just write out the first few. So we need, let's see, 4 over n, that was the inner product we found, divided by the norm of, right, the norm of the basis function that we're on, the square of the norm. But for all of the sine basis functions, the square of all their norms is pi. So we just get pi here. I, for some reason, became concerned that I missed something, but I think I got it. Okay, so times the basis function, which is sine x, right? Now we skip the even multiple 2x and go straight to the odd one. Oh, sorry, n is 1 in this case, so this is just a 4 up here. Okay, so next we go to n equals 3, so that's going to give us 4/3, 4 over 3 pi. Right? The 4/3 is from the inner product, and then the pi in the denominator is from the square of the norm, times sine of 3x, and so on, plus 4 over 5 pi sine 5x, etc. So there's our Fourier series. Let's see what the graph of this looks like. So let me pull up GeoGebra. And remember the graph that the graph that we started with. So the graph of the original function is this square wave. Okay, so let's graph this thing. 4 over pi times sine of x. That doesn't look too much like our square wave, although, you know, it is positive when the square wave is positive and negative when the square wave is negative. Remember, we're going from 0 to 2 pi, so 2 pi is just a bit bigger than 6, so keep your eye on this. And remember, the square wave is 1 up until pi, and then drops down to minus 1 until 2 pi. Okay, so the next term is 4 over 3 times pi times sine of 3x. Okay, now that is starting to look flatter at the top and at the bottom. Okay, so let's do a couple more terms. Plus 4 over 5 times pi times sine of 5x. You can see the more terms we add, the flatter the tops and the bottoms get. So let's do one more maybe. 4 over 7 times pi times sine of 7x. Okay, you can see this is starting to get quite flat on top and quite flat on bottom. Also, the transition from high to low is getting steeper and steeper the more terms we add. So you can see if we added all of the terms in this Fourier series out to infinity, all of the odd terms for sine out to infinity, the function that we get would approach closer and closer the the square wave that we started with. So it's in this way that the Fourier series represents the original function.